All right, boys and girls, welcome back to the drive-through. Hope everyone's having a wonderful afternoon in a special What Have I Gotten Myself Into edition of the drive-through, as these are starting to get kind of difficult. Okay? Thanks to my boy Devin, who I found his free YouTube subscription video and saved myself $20. And Devin, I was impressed, so thank you. And you get it. I'll give you a free sandwich, just salami on white with yellow mustard. Okay? All right. So today we're going to talk about curvature and arc length. And let's first start out by reminding you something that you learned in Chapter 9. I apologize. Unfortunately, S stands for arc length, and I cannot explain to you why that is. But I promise you that I didn't choose that. Okay? You did already learn this in Chapter 9. If you wondered why this happened in Chapter 9, Chapter 9 you guys did a lot of polars. Okay? Polar is a type of parametric function, and that's how you learned how to do this. But now we're going to apply it to our space curves and our plane curves. So, for a plane curve, S is the integral in between A and B of the square root of x prime of t squared plus y prime of t squared dt. And then if we have a space curve, then it should translate easily that it's x prime of t squared plus y prime of t squared plus z prime of t squared dt. Okay? So let's just start by talking about that. You've got some curve. Okay? Remember that as vector-valued functions, these curves are just the endpoint of a bunch of vectors over time. You got that? Okay, now what we learned yesterday was that at each point we can find a tangent vector, and that would be r prime of t. So let's remember that this red curve is defined by r of t equals, in this case, x of t comma y of t comma z of t. There is a vector-valued function, okay? So think about this. The derivative x prime, y prime, z prime is represented by this pink vector. It's the direction of our motion at each point, okay? If we took the limit as this delta t approached 0, it's starting to look like an integration. Can you sense that? Okay? So what we're doing is we're adding up. We're taking this thing that's curved, okay? And we're adding up a bunch of really, really small straight pieces. That is what the integral and the dt represent. So now we've got to understand why are we, and the derivative here, okay, gives us this tangent function, which is what makes this straight line in the direction that we're going. So the question might become, why are we square rooting and squaring? Okay, well, I think I can explain that. Think of, like maybe, I'm trying to see on my curve. At this point here, it looks like my unit vector is kind of headed in that direction. Not my unit vector, my tangent vector, okay? But let's say at this point right here, the tangent vector is heading in the opposite direction. Or think of this path, a spiral. if something was spiraling, well, if we were just adding the little tangent vectors, at one point the tangent vector might be going in this direction, and at a different point it might be going in that direction. And if you add those, you're going to get a net 0. So over the course of this path, if we just simply add them, we would get that our particle traveled 0 distance. So what we have to do is consider all the positive values, because we only want distance. That's why we're squaring them and square rooting them. Okay? So that's the first piece of understanding curvature, is understanding arc length. So far, so good? Okay, so here we go. The second part is now understanding what the heck curvature is. Okay? A few things that you should I want you to know. We're going to be able to prove these. I'll give you this proof tomorrow, but the first thing I want you to know is we kind of use some funky K, which you guys might know what that is. Is it a kappa maybe? I don't know. For curvature. Okay? So that's curvature. And the curvature of a circle is equal to 1 over r. So the first thing you should understand is that not all circles have the same curvature, which is very interesting. You would think that circles are similar to each other, but now think about walking around a circle whose radius is 3, and how that would make you feel compared to just walking in a straight line. When you walk in a straight line, you're currently walking around the Earth, so you are indeed walking around a circle. So now you can sense that different circles have different curvature, and the bigger the radius, the what? The smaller the curvature. Okay? You get that? So that'll help you get an idea of what curvature is describing. Okay? If we take our same position function, now what we're going to do is use our unit tangent vectors, and we're going to compare those to the distance that we've traveled. Okay, so you should know that in general, curvature is change in a unit tangent vector over, well, I'll just leave it delta. Change in s, where s is your distance traveled, your arc length. Got it? So I think I'm actually now capable of explaining this to you. At some point t right here, okay, sorry, at some point lowercase t, okay, no, this should be change in uppercase t. I'll explain it right now. Ready? If I promised you that that pink vector was 1 unit long, would you buy that that was the unit tangent vector at t? Okay, good. Now, let's say this was, so let's see, this pink vector right here is t of t. You good with that? Now let's say this is t plus 0.1. So we've just increased a little bit of time. And now, shoot, that wouldn't be it. You can see that it's changed just a little bit. Do you buy that? Do you buy that? Okay, so what this would be is capital T of t plus 0.1 right here. Well, all along I wonder, like, what does it mean these vectors have no position? Like, that always bothered me. And now I start to understand why that's such an important fact. If I took this t of t plus 1 and I redrew it, remember, they're both exactly a unit long. Do you see that that's about where it would be? So I've moved this thing over here. What I want you to think about is this blue vector that's in between those geometrically, that is t of t minus t of t plus 0.1. It's the change in our unit tangent vector. Do you get that? You remember how I made you geometrically represent these vectors? Now, if you didn't ever understand that, I'm not going to be able to help you understand this curvature. Okay? So right there, you would say delta t, and then what delta s is, let's see, we'll put that in green. That's delta s right there. That's how much arc length we've traveled. You can imagine that at that point, delta t over delta s would be pretty small. There's not a lot of curvature there. Now, take a look over here. Let me just buy myself some space. So let's see over here. We had another curve, okay? And let's say here we calculate capital T of t. This is now a different time, okay? You can see that here our unit tangent vector is going in about that direction, and it's about ready to change significantly. Now let's say I kept my delta s the same. So I'm trying to envision about that length of an arc. So maybe that would be like right around here. So now this new t is t plus 0.1 again. I'm just making that up. I've just increased t a little bit. Well, now you can see, I'm trying to see like where the, I think it'd be on this, maybe on this end. Do you see how that, stay with me here, I'm almost done with this little part. Do you see where our unit tangent vector is at this point? Do you agree that I wrote it correctly? So now check this out. If I, remember, vectors have no position. If I take this vector and I move it to here, it looks like that. Now what do you notice? Anybody notice what I want you to notice? Look at the delta t. Can you see it? This right here is delta t. Do you see it? It's really big now. And delta s hasn't changed. That's exactly right. This is much more curvy because the change in the unit tangent vector compared to the change in arc length is big. Where here, this right here is the change in the unit tangent vector. It's barely changed. And there you can see my curve isn't curvy at all, and there it's very curvy. That's curvature. Okay, and you can imagine for a circle, if we drew a little circle, there's not a whole lot of S there. There's not a whole lot of arc length. You're fighting it, Misha. I respect it so much. I've been there before. Okay? There's not a whole lot of S there, and there's a whole lot of change. So that unit vector might look like this. And here, this unit vector might look like that. Okay? And it hasn't gone very far at all, and it's changed. Whereas if I looked at just an excerpt of a humongous circle, let's say that was just a piece of a circle, and my unit vector is still the same length. I got that. I got that. When I put them together, there's not a whole lot of change. Can you envision that?
What if you put your second one further around? Wouldn't someone be thinking in opposite direction?
Okay, so you wanted to put it on my smaller circle. The question is, if I put it on the other side, it would be doing that, right? the curvature wouldn't have changed. The delta t would certainly have changed, but the s on the bottom, the delta s, would have also grown. Ironically, they would have grown totally in proportion to the radius. So that's why the curvature on this circle is constant. Every single place it has the same curvature, but that makes sense, right? The circle is the smoothest curve that there is. And the curvature on this huge circle is the same. It's just smaller. This is, for the record, why I don't lecture in class, because this is the second person sleeping. It's just so hard for you guys to stay awake. It's all right, Shiva. Don't worry about it. Okay, so hey, if you followed along with all of that, you're in good shape. Okay, now I want you to know that you will be given page 828 for your test, so you don't need to memorize any of the things I'm about ready to write down for you. Okay, so some formulas for curvature. Well, it's the magnitude of the unit tangent vector's derivative only if we are taking it as a parameter of arc length. So some of you asked before, well, what's the point of finding the arc length as a parameter? It makes the curvature easier. But we are not going to use that method, or I'm not going to use that method in class, okay? Unless we are giving something that has arc length as the parameter. So that one is not going to be that useful, but I would be failing you if I didn't include it in the class, okay? We will be using these. And I'll just pause the video and come back and kind of point out what they are. All right, look, so from page 828, we include these now, I've added since the pause, okay? Remember, the top one, that's only if we have arc length as the parameter. That's not going to happen very often. These bottom ones are all with time as the parameter. That's what we're used to. The only thing, you can use any of them. You should use the best one. But the only thing I want to point out is you cannot use the cross product equation in 2-space. Because remember, the cross product has to be in 3-space because it gives you a vector that's orthogonal to these two vectors, okay? So this must be a space curve. The other ones you can use in either scenario, space curves or plane curves. Now, you'll also see some equations that are specifically for plane curves. All right, wrapping this up. Look, these are only in a plane, and these are not either-or options, okay? So the top one, that's how you would find curvature in a plane if you were given a function y equals a function of x. Okay? And the second is in a plane if you've got a parametric where you have x equals x of t and y equals y of t. Okay? So hopefully that helps you read what's on page 828. What we haven't gone into yet is the applications of curvature, which is the whole reason we're learning it. So we'll make that video maybe tomorrow or on Monday. Your test is in a week. Can I get a boom, class?